Okay, good evening, everyone. This is the third tutorial session for the NPTEL course on variational calculus and its applications in control theory and mechanics. I am J.R. Krishnachan Avatar, a PhD scholar at the Indian Institute of Science, uh, and my my PhD is in aerospace engineering. So let's begin with today's session. Let me first present, as usual, the overview of what we are going to discuss in our today's tutorial session. We'll start with a brief review of what all has been covered in week 7 of this course, and they include Hamiltonian formulation, Hamilton's equations, and Hamilton-Jacobi equations. And thereafter, we would be following it up with several solved examples. Okay, so we begin with the first uh, topic, which is the Hamiltonian formulation. So as you recall from the last tutorial session, the concept of Hamiltonian has been introduced earlier in our course, in this course that we are currently running, in various forms such as Beltrami identity, and in variable endpoint conditions, and also in Brocken extremal. And so in this case, right now we would be making a connection between the Euler-Lagrange equations that we had derived with the Hamiltonian that we're going to discuss further. And one such transformation is called Lagrange transformation. Shortly, it's abbreviated as LT. So this is a transformation which makes a connection between the Euler-Lagrange equations and Hamiltonian of a problem. So let's consider LT involving a Lagrangian function, which is a function of T cube vector and Q dot vector. And Q dot vector uh, here is uh, here consists of n components. So I'll write it as Q vector is equal to Q1, Q2, and Q1. These are also known as generalized coordinates. And we define a quantity called pk, which is mathematically expressed as the partial derivative of fl with respect to qk dot to give the pth component of the p vector. Sorry, the kth component of the p vector. Now this equation here can be solved for qk dot in terms of p, provided that the Hessian, which is m, is equal to double derivative of f, uh, the double partial derivative of L with respect to Qi dot and Qj dot, provided that if the Hessian matrix is non-similar, then we are able to solve Qk dot in terms of Pk. Fine. In Newtonian mechanics, we define Pk as generalized momenta, Qk as the generalized coordinates, which can stand for anything, say displacements, angular displacements, uh, and also and then the Lagrangian is defined as the kinetic energy minus potential energy, and you see that kinetic energy is defined as T. Is mathematically represented by T, which is a function of small t, which is time, and Q vector and Q dot vector. And potential energy is a function of time and Q vector, which is the generalized coordinate vector. Okay, so let's review the Hamilton's equations. So given a functional j for qk vector, q vector, and this functional is defined as integral of L over T is equal to T naught to T is equal to T1, where Q vector is equal to Q1, Q2 to Qn. And L is, you are very familiar now that L is also the Lagrangian. Now, what we had called generalized momenta, and this, let's call it also as conjugate variables. So Hamilton's equations uses this concept of conjugate variables, and it's nothing but the generalized momenta for our case. And for this, the Hamiltonian is constructed as H is equal to summation of PIQI dot over all the indices, which is I is equal to 1 to n, minus the Lagrangian. And we can then derive the Hamilton's equations, which are also the canonical Euler-Lagrange equations in generalized coordinates, as Qi dot is equal to partial derivative of H with respect to Pi, and Pi dot as minus of partial derivative of H with respect to Qi. So essentially what we say is, given a functional as the functional we have here, this the extremal of this functional is going to be a vector, isn't it? And whose components themselves are functions of t. So essentially, since it's a functional of multiple dependent variables and one independent variable, so this would give us n second order ordinary differential equations in t. So, and that was also our Euler-Lagrange equations. All the and now what in Hamilton's equations, what we say is we are able to convert, or we are able to essentially convert. Yeah, so it's essentially we are able to convert n Euler-Lagrange equation in terms of 2n first order ordinary differential equations. Okay. Now let me talk about symplectic maps. So symplectic maps are canonical transformations. So what are canonical transformations? So canonical transformations are maps which change coordinate system. Fine. Okay. Say uh, okay, let's say when we are moving from Cartesian to polar coordinates, all that involves is change of coordinate system, isn't it? But and so here maps which change coordinate system but preserves the Hamilton's equation. You see the point, right? So what are symplectic maps? They are essentially maps which change coordinate system but still preserves the Hamilton's equations. Okay. So it's essentially a transformation from one phase space, which is Q vector, P vector, to another phase space, which is capital Q vector, capital P vector, where the components of the capital Q vector is uh, Q vector, which is a function of T, Q vector, small q vector, and small p vector. And likewise, the generalized new momenta, which is capital Pk, is equal to is a function of T, small q vector, small p vector. So what we see is such that the upon transformation, the Hamiltonian system transforms into another Hamiltonian system. So the original Hamiltonian system was H T small q vector and q dot. Sorry, let me write it as should be a p vector. So H small q vector, small p vector transforms into another Hamiltonian system, which is H hat, and its whose arguments are T, capital Q vector, and capital P vector. So essentially, there is a relation between both the Hamiltonian system, and it is given as H cap is equal to H plus partial derivative of phi with respect to t. Now, so we have introduced a new function. So here phi is a smooth function, which is also known as a generating function. Essentially, we require the generating function to to transform or move from our from the formulation of for Hamilton, I mean, or the Hamiltonian formulation in one phase space to that in the to moving into another phase space. So what we essentially require is phi, and what and we can deduce the generalized momenta in both the phase space from our phi here. Okay, I'll just call it. It's just phi. So pk is equal to partial derivative of phi with respect to qk, and capital Pk is capital Pk is partial derivative of phi with respect to capital Qk. Essentially, this is what we obtain using our generating function. Now let me talk about our Hamilton-Jacobi equations. So Hamilton-Jacobi equations are first order non-linear PDE whose solution gives generating function phi. So once a general solution to Hamilton-Jacobi equation is found, then we can obtain our solution to the Hamiltonian system. And this can be done using the help of the generating function in the form of an implicit equation, isn't it? So this generating function essentially gives us the helps us to obtain solution of our Hamiltonian problem. So the Hj or Hamilton-Jacobi equation is given by capital H, which is the Hamiltonian. So capital H, and which is a function of t q vector and partial derivatives of phi with respect to all the generalized coordinates q i's plus partial derivative of phi with respect to t is equal to 0. So this is our Hamilton-Jacobi equation. So now let me talk about the conservative systems. So what are conservative systems? So if I ask you, what you'll say is from a mechanics point of view or from a thermodynamic point of view, conservative system is a system whose total energy, or in that case, the thing is we define conservative system. One is from a point of say if the energy of a system remains constant. That's another thing. And another way that we often talk about is one way what we call is conservative force. The conservative force is a force which is defined as a gradient of some scalar function. Or otherwise, if the work done to take a point from one to take a body from one point to another point in the presence of some force, and if that work done only depends of the endpoints, isn't it? Only at the points. So that force is also called a conservative force. For example, one such example is the gravity, force of gravity, isn't it? So if you take a body from one point to another in the presence of gravity field, what we say is the potential, the energy that the body acquires, nothing but the difference of the energy at both the points, isn't it? So that's what we just, it was a slight digression. So that's what we call as conservative systems, and how we define conservative systems from the point of view of forces and from the from energy perspective. Now, Hamiltonian H does not depend on T explicitly. So this is how we look, or how we see from a mathematical point of view, that when the Hamiltonian doesn't depend on T explicitly. So this implies that H is a function of Q vector and P vector. Okay. Okay. And so what we see is H is constant along any extremal. So when we put this conclusion or put this reduction in the Hamilton-Jacobi equation, then what we have is partial derivative of phi with respect to t plus h as a function of q vector and p vector is equal to 0. This implies that partial phi by partial t is equal to minus h q vector p vector, isn't it? Now, this quantity here is just a function of time, is a function of time, isn't it? Or otherwise, what I would call is, or let me go the other way around. So this quantity here is not a function of time. No, you'll say that fine, but q vector and p vector can depend on time. So let me rephrase it. It's not an explicit function of time, or it's not an explicit function of t. So this means that del phi by del t, if it contains t, then this is a function of t. Say this is a function of t, and this is not a function of t. So for both the things to occur in general, the only way for this equivalence to be true is when both the terms are equal to some constant. And that's what I call as minus of f of alpha. Now alpha is some constant, isn't it? And f is a function of that. So this implies that phi upon integration, let's integrate this equation, isn't it? Del phi by del t is equal to minus f of alpha. Upon integration, what we have is p as a function of t q vector is equal to minus f of alpha t, and plus psi, which is a function of q vector alpha. Okay. So now let's take the second equation, which is h q vector p vector is equal to f of alpha, and this is constant along an extremal q vector, which is a function of t, alpha, and beta. Right. So this gives us the reduced Hj equation, and this is nothing but restatement of what is seen here of this statement. Right. So with this, we have covered the review part. Okay. And so what we went through is we started with review. We discussed Hamiltonian formulation, then went through Hamilton's equations, and then into symplectic maps, and Then we discussed about Hamilton's equations and problems with our systems which are conservative in nature. Okay, so let us now start solving some solved problems. Okay, so we begin with the first question. First question. So we begin with the first question. So the first question says that consider the functional j, which is a function of x and y. This is defined as t naught to t1 root over x squared, x dot square plus y dot square, and where x and y are functions of the independent variable t. Okay. Use transversality condition to find the curve which has the shortest path from the origin to the line -2 minus x. Fine. So let's begin solving this problem. Okay. So at first, let me state the integrand of the functional. So we'll denote it by f. F is equal to root over x dot squared plus y dot squared. Right. So what we clearly see that this problem has one independent variable and two dependent variables. So when we derive the Euler-Lagrange equations, EL equations, we'll have set of two Lagrange equations. And the first one is del f d by dt of del f by del x dot minus del f by del x is equal to 0. This implies that d by dt of, and what we clearly see here is df by dx, del f by del x is 0, isn't it? So we have, and so essentially what we see is, so this means that d by dt of del f by del x dot is equal to 0. And this implies that del f by del x dot is equal to some constant c1. And this is nothing but x dot by root over x dot squared plus is equal to c1. And now the second Euler-Lagrange equation, which is d by dt of del f by del y dot minus del f by is equal to. So similar to the previous Euler-Lagrange equation, this is also going to be 0, and then we'll just have del f by del y dot is some function is equal to some constant c2. So essentially this implies that y dot by root over plus y dot squared is equal to c2, isn't it? Now let's name this equation 1 and this as equation 2. So divide 1, divide 2 by 1, and then this leads us to y dot divided by the thing is the denominators in the both this cancels out, so we'll have y dot by x dot is equal to c2 by c1, and the ratio I just call it m. Now this implies that then let's write y dot in the form of the ratio of derivative of differential. So dy by dt divided by dx by dt, isn't it, is equal to m, and this is nothing but dt cancels out, so we have dy by dm, no, dy by dx is equal to m. So this is a first order differential equation. Upon integration we'll have y is equal to mx plus c, right? So we have two constants essentially, isn't it? So we have two constants. So we have two constants, which are m and x. Sorry, m and c. M and c are constants needed to be determined. Okay, both are needed to be determined. Now let's use the one end condition. And the one end condition, which was that the transversely condition to find a curve which has the shortest path from the origin, right? It says from the origin. So this implies that x at t naught is equal to 0, and this is also equal to even y at t naught is equal to 0. So this was one of our this is one of the two end condition, right? First end condition is known. The other end condition is 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 variable. However, the other end condition is required to only move along the line y is equal to -2 minus x. Okay, so using our use first end condition, I'll say, or I'll say use non end condition. So which is essentially at t is equal to t naught, y is equal to 0, and m into x is also 0 plus c. So this implies that c is equal to 0. Okay, so we have obtained the first constant, which is c is equal to 0. Now we need to determine the second constant, which is m. Fine. So to do that, we need to use the condition for the variable endpoint condition, but in this case, more specifically, we have to use the transversality condition. Okay. So what I do is, let me first begin with taking the condition for transversality, right? The transversality condition. Although this is, I'm using the more general form of the variable and condition, but I'll just denote, okay, fine. So it's transversality condition. We'll start with the endpoint condition says that pk del qk, and in this case we have two dependent variables, so it is k is equal to 1 to 2 minus h delta t is equal to 0. We can just expand it, right? We'll just call it p1 delta q1 plus p2 delta q2 minus h delta t is equal to 0. Let's contextualize it in our problem. So Q1 is nothing but X and Q2 is nothing but Y in our problem. Fine. Now our goal is to determine P1, P2, and H. So we define from our definition. So P1 is given as del F by del X, isn't it? Sorry, del X dot, isn't it? So this is not, this is X dot divided by X dot squared plus Y dot squared. Likewise, P2 is partial F by partial Y dot is equal to Y dot divided by root over X dot squared plus Y dot squared. Fine. And H is given by summation, or what I would call is P1 del X dot plus P2. Sorry, it is P1 X dot plus P2 Y dot minus F. So let me just copy this to bring it to onto the next line. So this is essentially, so P1 into X dot is X dot squared divided by root over X dot squared plus, similarly P2 Y dot is Y dot squared divided by minus root over X dot squared plus Y dot square is equal to. Now, from the first two terms, what we see, the denominators are common. So we can just add the numerators. So this gives us X dot squared plus Y dot squared divided by root over X dot square plus Y dot square minus root over X dot square plus. So this essentially, this term essentially gives us root over X dot square plus Y dot square, isn't it? So essentially H is 0. Okay. So now our transversality condition is P P1 del X plus P2 del Y is equal to 0. And this implies that, so this implies that P1, which is X dot divided by X dot square plus Y dot square. And now mind you that this actually is for, I should have mentioned it, I'm sorry for being very late. It is actually at T1. Fine. So this holds at T1. And into del of X plus Y dot by at T1 is equal to 0. Because the complete expression at T is equal to T1. Now what we see is the denominator in both the cases, for well-defined X and Y, we won't have the denominator to be 0 at any point. Or for a regular, which just say that X dot and Y dot are required to not be 0 at the same time. So this means that the denominator can just be factored out and then taken to the other side of the equation. So this is essentially X dot X plus Y dot del Y by A at T is equal to T1 is 0. Now let's bring in the the constraint that we have for the endpoint, isn't it? Which is that it can only move on the line y is equal to minus 2 minus x. So which simply implies that the variations in x and y are not independent. So one is dependent on the other. So what we say is, so at t is equal to t1, at t is equal to t1, we'll have y is equal to minus x, or yeah, minus x minus 2, isn't it? So this implies that even the variations at t is equal to t1 will just have del y is equal to, we'll apply the variation operator, which is del here. So variation in y is equal to minus variation in x, and mind you that del of 2 is 0 because these are fixed numbers where no variations are possible, right? So this is the relation between del x and del y. So this equation eventually, this equation becomes x dot and plus, sorry, x dot, yeah, plus, and I'll just substitute this relation there, x dot minus y dot into del x at t1 is equal to 0. So for arbitrary variation, this implies that, I'll just call it as, uh, for arbitrary variation, obviously delta x cannot be 0, right? Del x at t is equal to 1 is not 0 for arbitrary variations. So this simply means that x dot is equal to, or x dot minus y dot at t is equal to t1 is equal to 0. So this is our conclusion from here, from this statement, from this mathematical statement. So now what we can do here is, uh, we had determined y dot, in terms of, from the equation here, we had determined y as a function of y as a function of x, right? So then what we say is, given that given y is equal to mx, so our goal was to determine the value for m, but so we'll use this condition to obtain the value of m. Now we'll differentiate both sides of this equation with respect to t. So this gives us y dot is equal to mx dot, and then at t is equal to t1, we'll still have x dot minus mx dot at t is equal to t1 is 0, and then this gives the 1 minus m x dot is equal to, again for general x dot, for general curve x dot will not be 0 always, right? That's one law, one way of looking at it. So had x dot in 0, and then what, and then that simply means that x should have been a constant, because the thing is we are dealing with a linear equation, right? So then even y would be a constant, so which is not possible, right? So the only other conclusion is m is equal to 1. So therefore the extremal is y is equal to x. Okay. Now if we draw this figuratively, what we have is, let's draw the line y is equal to minus x minus 2. So at x is equal to, at y is equal to 0, x is equal to minus 2, right? So it's this point. Likewise, at y is equal to 0, at x is equal to 0, y is minus 2. So y comes here. So we'll have a line which passes through both these points. Now we are asked to find the shortest, the a line, isn't it? So we are to require we are required to determine the shortest path which connects the origin and touches the line y is equal to -2 minus x, given this x and y, and these are origin. So what we see is, so this is the line. This is our y is equal to x line. And then you see is from the very from our maths learned in high school, what we see is the slope of this line is 1 and the other line is -1. So essentially the product of the slopes are 1 -1, so which essentially mean that one line is orthogonal to the other at the point of intersection. Okay, so now let's move to solving the next question. So the next question is that we are to consider a mass m attached to a spring k, which is executing simple harmonic motion, or simple harmonic motion, sorry. So it's a simple harmonic motion. And we are required to derive the corresponding Euler-Lagrange equations. And then furthermore, we have to construct its Hamiltonian and obtain the Hamilton's equations, right? So let's go let's solve this problem part by part, right? So let me first draw a schematic of the problem. So the problem is that there is a fixed wire and spring is attached to this, which is one end is attached to a mass m, and this mass is oscillating over a frictionless surface, and the spring constant is k, right? So at first construct we need to construct the Lagrangian. That's the base, okay? Let's determine the kinetic energy of the system. Now, as the mass oscillates, so the mass has inertia, right? And you know that the kinetic energy is due to inertia. So the kinetic energy will be denoted by T. This is defined as half, and then let me also so it's oscillating. It's executing a horizontal oscillation. So half m into velocity squared. And then due to extension in the spring, there is a elastic energy. So there is an elastic strain in the spring, so which produces some restoring force. So because of this, this spring tends to have something known as potential energy, but to be more specific, it is nothing but strain energy, right? But we still call it as a potential energy. We denote it by capital V. This is equal to half kx squared, right? And as we had learned in the review, the Lagrangian L is given by T minus V, which is half mx dot squared minus half kx squared, right? So we have determined the Lagrangian. Now let us determine the EL equations. So this problem has one independent variable, which is time. So x is a function of time t, and one dependent variable, which is the displacement variable, which is x. So we'll have just one Euler-Lagrange equation, which is given by d by dt of partial L of x dot minus partial L by partial x is equal to 0. And this implies that d by dt of mx dot minus kx is equal to 0. This implies that mx double dot plus kx is equal to 0. Fine. So this was our Euler-Lagrange equation. Now let's construct its Hamiltonian. So the Hamiltonian is defined as H is equal to P into, I'll just call it as x dot, P into x dot minus L itself, right? So P is given as del L by del x dot, right? So this is the expression for P. So it is half mx dot. So mx dot into x dot is mx dot squared minus of half of mx dot squared. So this gives us, I just write in the expression. So it is half mx dot squared minus half kx squared, and this gives us mx squared, mx dot squared minus half mx dot squared is half mx dot squared and plus half kx squared, isn't it? So this is our Hamiltonian. Now we are asked to determine obtain the Hamilton's equations. Okay, so we move to obtain the Hamilton's equations. Hamilton's equations. So the Hamilton's equations was, what were the equations? That Qi dot is equal to del H by del Pi, and Pi dot is equal to minus a partial H with respect to Qi. So what we do is let's formulate our H in terms of P and X here. So I'll just call let let Q is equal to X is equal to then this implies that H is equal to, so here this we have to manipulate in terms to obtain the terms in what you call Hamiltonian in terms of Q and X dot. Okay, so H is equal to mx dot whole squared by 2 into m plus half k q squared is equal to what? This is equal to p squared by 2m plus half kq squared, right? So we have obtained our Hamiltonian in terms of p and q, or in terms of generalized coordinate and generalized momentum. So the first first Hamilton equation is q dot was equal to del partial h with respect to p. So this gives us p by m, right? So this gives us 2p by 2m, so it is p by m. And the second Hamilton equation is p dot is equal to minus del h by del q. So this gives us minus of, again, 2q cancels, 2 cancels out, so we'll have minus kq. So Essentially, these are equations, Hamilton's equations. Now let's move on to the third question. If you want to show the equivalence, then that also we can do. Let's differentiate. I mean, this is just a side note. Just equivalence, right? Equivalence between this and this. So this gives us. We'll differentiate the first, or we'll just substitute the expression for p dot. So p dot is mx dot double dot, right? Because m is a constant, and minus k, and q was nothing but x. So you see that we have obtained the original equation mx double dot plus kx. Just to show the equivalence between both the Euler-Lagrange and Hamilton's equations. Now this problem, the third problem, asks us to show that the total energy of a mass spring system is constant. But let me add something more here. That here we know this fact very well, but this is just to show that it's constant using HJ equations or Hamilton-Jacobi equations. So what we have seen is, so far in the previous question, we were able to obtain our Hamilton equations, right? Or the Hamiltonian of the equation of the system as a function of QP, right? This was a function of QP, and this was P squared by 2m plus half k q squared, right? So now let's bring our HJ equation, right? Or essentially it was just single equation here, but so it is just HJ equation, right? HJ equation. And this was given as del partial phi with respect to t plus h, as I'll write in terms of hq, is equal to 0. Now we'll use the argumentation that we had, the argument that we had utilized in our review, which was to say that h here is clearly independent of, I mean here, h here is clearly independent of right? It's explicitly independent of t. So then, yes, so what we are dealing with is a conservative system, isn't it? And that just from the fact that h is independent of t. So this implies that del phi by del t is equal to minus h qp. Now, mind you that this is independent of t, right? Not a function of t. Not a function of t. Not a function of t. This may or may not be a function of t. In general, it is a function of t. So for both these quantities to hold equal always, what we are required is this is to be equal to some constant minus alpha, isn't it? Now what I do is I just choose the last two, this equivalence here. So then this implies that h qp is equal to some constant alpha. But you know that this constant has to be determined using certain initial conditions of the system, right? So alpha needs to be determined some state, I'll call it in general, from some state of the system. because since it's a constant, it holds at all states. So even the properties at one state is enough to uh, determine the value of alpha. So what we see is HQP. So essentially, it is p squared by 2m plus half kq square is equal to alpha, right? So this quantity is the expression for total energy. Why? Because this term denotes kinetic energy and this is potential energy at all states, which is parametrized by mathematically parametrized by t or time. So since this equivalence, so since this equation holds at all t, we say that the total energy of a system is constant, of a mass spring system is constant. This is just a very simple example. Now let's move to another problem here. So here a particle of mass m is moving vertically under the action of gravity and resistive force numerically equal to c times its velocity y dot. So it asks that what is the form of its Hamilton's principal equation? Okay, so I think you have understood the problem here. So the question says that you have to determine the first thing is it's moving vertically under the action of gravity. Fine. Say a particle of body mass. Say it's moving vertically under the action of gravity. So gravity will pull it down. Okay. And there's a body m of mass m. And it's say falling at some velocity of y dot. So this is falling at y dot. And I'll fix, you'll ask me, okay, where do I fix the coordinate system? I'll just fix the coordinate system, the origin here, and y downwards. So it simply means that I'll take the position from where it started, or from where the body was let off, to be the origin of our coordinate system, and y is pointing vertically downwards. Now, what we'll have is let's determine the total potential energy of the system. Okay. First, we'll start with kinetic energy, which is denoted by T is equal to half of mx dot squared. I have not shown a free body diagram, right? The thing is there is a mass m, gravity is acting downwards, and there is another resistive force which is numerically equal to c y dot. So c into y dot, and it is opposite to the direction of the motion of the body. Okay. And now what I do is what I'll do now is I'll construct the potential energy of this body. Okay. Now you'll ask that, okay, but now when the thing is, the energy is usually, so potential energy V is equal to mg into some distance, right? But then you'll ask me, but why is the potential increasing, potential energy decreasing, right? So why is the potential energy decreasing as the body falls down? Okay, so that can be elevated. This requirement can be elevated by just putting a minus sign before the. Can be taken. So this requirement can be taken into account by adding by prefixing one negative sign to this expression mgy. And the other thing is what we are asked to do is to find the resistive force. Okay. Now the resistive force is minus cy dot, isn't it? So the virtual work done due to this is is nothing but minus cy dot to del y. I should have been y here. Yeah. So the Hamilton principle says that. So I'll write the Hamilton's principle now. States that over an interval t0 to t1, del w external, or I'll just call it NC, non-conservative, plus del of t minus del of v. Integral over dt is 0. So then this implies that there may be a sign convention issue here. It depends on the definition of what we say, right? So if it's work done on the system, thermodynamically work done on the system is negative. Sorry, work done on the system is positive, and work done by the system on external bodies. I'll just confirm this. So now the work done for the system on the surroundings. The work done on the system by its surroundings is positive. That is by IU pack. But in mechanics, what we do is mechanical engineering. We take work done is taken to be positive when work is done by the system on the external. Okay. So here the thing is that there is a work done by the surroundings on the body, right? So it is minus Cy dot. Yeah, so minus Cy dot del y. So this is consistent with. So then this from T0 to T1 minus Cy dot plus so minus Cy dot into del y plus I'll take del as common and then T minus V is, let me just write right now, it's just del WNC plus dt is equal to 0, and then this implies that T0 to T1 minus Cy dot del y plus del of half my dot squared minus V, so this becomes plus mg1. Fine. So this is our Hamilton's principal equation that the question asked us to determine. So now let's deal with with another question in this sequence. So the question states that three masses are connected in series to a fixed support. Okay. By linear springs. Let Qi represent displacement from equilibrium and Ki be the spring constants. Assuming that only spring forces are present, what will be the Lagrangian function of the system? So what we do is let's first construct the component energies of the system. Or before that, let me draw the schematic of the problem that will help us to easily formulate our mathematical expression for the component energies. So we have three masses unconnected in series to a fixed support by linear springs, right? So this is mass M connected to another mass, the third mass. And this is a fixed wall. The spring K1, spring K2, spring K3. And the masses are M1, M3.
Now what I'll do is also denote the displacement from equilibrium, right? So this is x1, the displacement of m1 from the equilibrium position, and for this x2 and x3. Now let's study the extensions between in all the springs one at a time. So extension spring K1 is what? When you look at it clearly, you see that one end is connected to a fixed wall. So there is no displacement of the end point of of the right end, or sorry, of the left end point of the spring at K1, while the other end point, which is the right end point, undergoes motion or undergoes the displacement x1. So the extension in spring K1 is x1 minus 0. And the extension in spring K2 is, here what we say is both the endpoints are undergoing extension, right? So here we need to look at the net extension. So net extension, I'll just call it x2 minus x1. Ideally, we should have say we should take the absolute value if we are worried about just the, yeah, because we are worried about just the extension. I'll just take it as the absolute value, x2 minus. And likewise, extension in spring K3, which are again connected to two masses undergoing displacements x2 and x3, the x3 respectively. The next extension will be absolute value of x3 minus x2. Okay. Now let's construct our the expressions for kinetic and potential energies. For the kinetic energy, which is whose this also is also denoted by is denoted by capital T, is the kinetic energy will be the sum of individual kinetic energies of the masses. So m1 x1 dots squared plus half m2 x2 dot squared plus half m3 x3 dot squared. Okay. And the potential energy, which is in our case, it is the elastic strain energy stored in all the springs. Now this is given by P, sorry, V is equal to half x1 x1 k1 x1 squared plus half of k2. Now the extension in the spring k2 is absolute value of k x2 minus x1. Now when we take the square of this quantity, it's the same as just taking the square of the signed extension, right? Or this extension with sign plus or minus. Likewise, for the third spring, we have half k3 x3 minus x2 squared. Fine. Okay. Now we can construct our Lagrangian. L is equal to T minus V. And this gives this is nothing but half m1 x1 dot squared x2 dot squared plus half m3 x3 dot squared minus of k1 x1 squared plus, sorry, minus half k2 Okay, so this was our our Lagrangian of the problem. Fine. Let us move on to solving the third uh, another problem in this sequence. So this problem states that a particle moves on the surface P xyz, which is a function of xyz, is equal to 0. And from the point x1 y1 z1 to the point x2 y2 z2 in time t. Okay. Now, if it moves in such a way that the integral of its kinetic energy over that time is minimum, determine the differential relation between the coordinates of the particle and the mass and the surface. Okay, so we have some surface. If I draw a schematic of the problem, so this is our surface, some arbitrary surface. Okay, and so we are so a particle is required to execute, and this surface is denoted by xyz. 5xyz is 0. From this and this point x1, y1, z1 to another point x2. So we are required to minimize the integral of the kinetic energy over that time. So our J is essentially, and let's take the mass of that particle to be m for the sake, right? So we are required to from 0 to t, okay, capital T, and we are required to minimize the kinetic energy. So kinetic energy, the expression for kinetic energy is half m x dot square plus y dot square plus z dot square. This is our velocity squared into dt. However, this problem has a holonomic constraint, right? Because and it has a holonomic constraint phi x y z is equal to 0. So we need to construct a subject to phi y z equal to 0 for all t is an element of 0 comma capital T. Mind you that to be more explicit, I should write as phi of xt, yt, z of t is equal to 0 for all y, for all t is equal to is an element of 0 capital T. So we construct an augmented functional. Okay. We construct an augmented functional. And this will be, I'll just call it as some capital F is equal to 0 to t of, or for now I'll just call it j plus. Okay. J plus. Now this holonomic constant has to be satisfied for all t, right? So even the Lagrange multiplier, which will enforce that constraint, is going to be a function of time. So lambda is a Lagrange multiplier, which is itself a scalar function. And then phi of x, y, right? So we'll just formulate and construct a combined expression. So it will be just half x dot square plus y dot square plus lambda is a function of t and phi
x, y, z dt. Okay, so let's call this as our Lagrangian L. Fine. So so what we see is this L here is the integrand is a function of the only independent parameter variable is t, and we have four dependent variables, right? X, y, and y, z, and lambda. Okay. So we'll have four Euler-Lagrange equation. So let's determine our Euler-Lagrange equation. So the first Euler-Lagrange equation is d by dt of partial L with respect to x dot minus partial L with respect to x is equal to 0. And this gives us d by dt of partial L with respect to x dot is 2x dot divided by m to m into 2x dot divided by 2. So it is mx dot, right? Minus del L by del x. Now, when we take a look at this expression clearly, so the only the only place where x occurs is as an argument to the function phi. So what we have is this will be given by so the derivative, so lambda into derivative of partial derivative of phi with respect to x is equal to 0, and there is nothing but mx double dot minus lambda. I'll just denote use this shorthand notation. So phi x is equal to 0. We can rearrange this term to get mx x double dot by phi x is equal to lambda by m. Okay. Now the second Euler-Lagrange equation is d by dt of del L by del y. Repeating the same procedure as above, we'll have d by dt y dot minus lambda phi, lambda into the partial phi with partial y is equal to 0. And then this implies that my double dot minus 5 to 0. This implies that pi double dot by phi y is equal to lambda by m. Fine. And the third Euler-Lagrange equation is, I'll just write the final expression. Similar to the previous steps, we'll just have z double dot by phi z. And the fourth Euler-Lagrange equation is d by dt. Now you'll say, okay, del phi dot, del lambda dot minus del L by del lambda. So del lambda dot doesn't exist, so this term is 0. So what we are left with is minus L by del lambda, and this is nothing but phi of x y z is equal to 0. This is just the constraint. So from equation 1, 2, and 3, what we see is for all these equations, we have the same term on the right hand side. So the conclusion is from 1, 2, and 3, we have x double dot plus p of x divided by equal to y double dot So this is our relation. So our relation or our goal was to obtain the differential relation between the coordinates of the particle and the surface, isn't it? So this is the equation that links the differential of the coordinates to the derivatives of the equation for the function for the surface, right? Okay. So I had planned to solve these many questions in today's tutorial session, and I don't see anyone in the audience. So let me find a few more problems to solve. Okay, so let me start with one problem. The problem is, let me state the problem. So determine the Hamilton's equations for Hannon uh, Hales problem. The Hannon's help, the Hamiltonian of this problem is given by whose, I'll just call that whose Hamiltonian is H is a function of PQ both are vectors, is equal to half p1 squared plus p2 squared plus half q1 squared plus q2 squared plus q1 squared q2 minus 1 by 3 q2 cubed. Okay, so let's so here we have the coordinates, uh, the generalized coordinates are q1 and q2, and the generalized momenta are p1 and p2. So, so how many equations will we have? So two for generalized momentum and two for momenta and two for generalized coordinates. So we'll have a set of four equations, first order ODEs, right? Let's let me write down the expression for the Hamilton equation. So Hamilton's equations are QI, I'll just write it here, is equal to minus, sorry, it's equal to partial H by, with respect to PI, right? Where I is equal to 1 comma 2. Likewise, Pi dot is equal to minus partial H with respect to Qi, where our I is again 1 and 2. I won't write it this. So let's start with Q1 dot. So Q1 dot is equal to, we have to take partial the Hamilton with respect to P1. So P1 we'll have 2 into P1 by 2, so we'll just P1. Fine. The second is Q2 dot. For this, we'll have to take a partial derivative with respect to P2. So it's again 2P2 by 2. So it is P2. And for the third, we have P1 dot is equal to minus of whatever comes out as a result of doing the operation partial derivative of H with respect to Q1. So then this gives us uh, 2 into Q1 by Q2 is just Q1 by 2, sorry, and plus 2Q1 Q2, right? Now for P2 dot, we'll have to take a partial derivative minus of the partial derivative of H with respect to Q2. So then this gives us 2Q2 divided by 2. So it's Q2 plus Q1 squared minus 3 into Q2 squared, right? 3 into 3 by 3 into Q2 squared. So it is Q2 squared. So yeah, these are our organizations. Now mind you that Hanon's formula is looks as a very although this expression looks very simple or not very complex, I would say, but then solving it with for various initial conditions Q1, Q2, and P1, P2 can, it does even produce very chaotic solutions. So this is a very rich problem. So let's discuss another problem called Kepler's problem. Kepler's problem. So write down the Hamilton's equations for the Hamiltonian, which is h is equal to h as a function of p vector. Q vector is half of p1 squared plus p2 squared minus square root of q1 squared plus q2 squared. Okay. So what we are required to do here is, let me first describe you what this problem essentially is. So this problem is a two-body problem essentially. So the schematic is goes as, given that sun is here, right? Sun is at one of the, you know, that the orbits in space, orbit of us of any space object is always a ellipse. Is always an ellipse. So what we are doing here is we are considering the motion of body around the sun. So the sun is located here, charge mass, and a body is revolving around it along an orbit. So, and we are just required to find the orbit or the trajectory uh, of the motion of this, or the trajectory of this body, or I'll just call it P1, or just P, or I'll just, let's just name it some A here, right? This planet A. This is our sun, and the coordinates of this of the planet A at any time t is q1 comma q2, q1 and q2, right? So we need to determine the Hamilton's equations for this Hamilton. Now, when we clearly look at the Hamiltonian, we see that we have two generalized momenta and two generalized coordinates. So we are going to get a set of four ordinary differential equations. Let's start the first one. So q1 dot is equal to p1, and this is just p1. And the second one is q2 dot is equal to, again, there is nothing but p2. The third is p1 dot is equal to minus del h by del q1. This is minus into minus plus, right? Minus into minus. I'll just put it minus here for now, and then minus into again. So this is half, so it is just plus plus half of q1 squared plus q2 squared minus 3 by 2 into
2 into q1, isn't it? So this effectively becomes 2 cancels out, and we'll have minus q1 divided by q1 squared plus q2 squared to the power 3 by 2. The fourth equation is minus, it will be very similar to the previous one. There's minus q2 by q1 squared plus q2 squared to the power 3 by 2. Now this set of equations can be solved subject to can be solved subject to some initial conditions. In order the initial conditions, they will denote as q10 is equal to q naught, or let's say we'll just call it a1. Likewise, q20 is equal to a2, and p10 is equal to a3, and p20 is if. Okay. So it seems that there is no attendee right now, and so there, since I didn't prepare enough material beyond this, so what we can do is we'll discuss other topics in the next tutorial session on on that coming Tuesday, which is 21st March. So with this, I'll just wind up today's tutorial session. Yeah, so thanks.